Yes, good afternoon, everyone. Good afternoon, everyone. I hope this finds you well and hopefully feeling refreshed after a summer break, if you were lucky enough to have one. I'm Emma Hudson, Chair of the ICT, and it's my pleasure to welcome you to our ICT webinar this afternoon. We're hoping that we should be able to get back to our ICT evening seminars at the end of this year, but maybe possibly start of next year. I know I've very much missed the face-to-face events and the chance to network and discuss the information disseminated during our evening seminars. But hopefully you will find these a suitable alternative while we're still limited on our meetings together. Our webinar will include 2 presentations today. We will then have a question and answer session with our presenters. So if you have any questions for either of our presenters, then please use the chat function and send these questions to me during the event. We do ask that everyone remains on mute during the call and that you do not use your video so we can focus our attention on our presenters today. The presentations we have for you today are Martin Wickham from the National Physical Laboratory in Teddington, who will be presenting on high voltage partial discharge testing of PCBs and coatings, and Ken Klapproth from CHASM Advanced Materials, who will be talking to us about advanced antenna materials for 5G. So to our first speaker, Martin Wickham from the NPL. Martin is a senior research scientist at the NPL and leads the electronic and magnetic materials team, who conduct valuable research and testing for our electronics industry. Martin is also instrumental in the standards development work for both IEC and IPC, and last year was awarded the IEC 1906 award in recognition for his role in the development of the IEC technical report 61189-5-506, which led on to the publication of the IEC SIR test standard 61189-5-501 in 2021. Martin will be sharing with us today the work the NPL have been conducting on the high voltage partial discharge testing of PCBs and coatings. So Martin, you've already got your screen shared, so please begin your presentation.
Thank you very much, Emma. Just to say that I'm team leader for advanced electronics within the group, and there are contemporaries of mine who would also claim to have equal leadership, so I won't claim to lead the whole group. But thanks for the intro, Emma. I'm sure we all recognise the push to higher voltages. We want to reduce our CO2 emissions with clean air, green energy, the push to automotive, aerospace, etc. in these areas, the changes in the infrastructure to charging stations that we've got, and the technologies that are being put in place at the moment to make the most of those changes. It's quite a very active area, particularly for funding, which is one of the reasons we're in it, frankly, in power electronics, in compound semiconductors, and there's quite a bit going on NPL with battery technologies as well. I'm sure we're all fully aware of the move to electric vehicles, the fact that automotive is somewhat ahead of aerospace at the moment, but it's all coming. And then there are a whole host of other areas that we need to look to address, not least, the whole public transport infrastructure, energy distribution, local energy distribution, solar power, etc. A lot of these power modules are essentially based on ceramic substrate options. So they're alumina, aluminium nitride, they're direct copper bonded, all that sort of material. And that's where most of the applications at the moment, particularly in the high voltage side, the silicon carbide side are. However, these applications are very high weight and they're relatively high cost as well for what's necessary. So there's a potential here as a market, I would hope, to look at the use of PCBs more within these structures. But there are reasons why people use ceramics in high voltage work, and that's to a large extent dictated by electrical discharge within the systems. So I'm sure we're all familiar with a full electrical discharge that happens in air at around 3 kilovolts for every millimeter of spacing you have between conductors. If you put a dielectric between those, PTFE for instance, you'll push that up to about 30 kilovolts per millimeter. And when it does break down, there's obviously a lot of flash bangs and wallops going on. One of the issue that we're looking to understand better at the moment is a phenomenon known as partial discharge. So this is where you don't get to those voltages, you don't get to your 3 kilovolts per millimeter, but you can still get a small electrical discharge or spark occurring within the insulator between two conductors. And particularly where that dielectric is organic based, that can lead you into problems. The PD can occur at any point within the insulation, and it's where the local field strength, electric field strength, exceeds the local dielectric breakdown strength. It can occur multiple times, and it will gradually reduce the dielectric strength. And perhaps I'll show you some examples, one of which is PCB based. It occurs in solids. It's really quite dependent on the sort of defects that you have within the dielectric, and ultimately, of course, it will occur across the surfaces of the insulation. So you don't have to just break down through the whole insulation. You can break down to a shorter distance to the surface, and then break down across the surface and back through the dielectric again. And it does occur in liquids and gases as well, within bubbles within those systems. The breakdown voltage in a gas is dependent on Paschen's law, which effectively, for the purposes of what we understand here, is that as you reduce the pressure of that gas, the breakdown voltage drops until you get to a minima, and then it starts to increase again. So it just happens that for the sorts of gases that we're normally used to dealing with in the atmosphere, this Paschen's minima is somewhere up a cruising altitude of aircraft. And so this is why the aerospace industry is particularly interested in this partial discharge phenomenon, because if it follows Paschen's law to any degree, they are going to see partial discharge voltages, or the inception voltages for those partial discharge, dropping as they climb in altitude. PD is related to a change in voltage with respect to time. So it's related to dV/dt. And so it's predominantly a phenomena associated with AC signals or switching power signals. And it generally occurs in the region where the change in voltage is greatest with respect to time. So that's in the up curve of an AC, a sinusoidal AC system. Obviously in a square wave, it's at the very start of the square wave, depending on how long it takes you to build to your voltage. And it can occur repetitively, it can occur on the plus and the minus side of the cycle. And it's well known within the power electronics or the power distribution industry that this PD can build, it can cause damage over time, and eventually ends up in breaking down the insulation resistance of the system. And again, hopefully I'll show you some brief examples of that later. One of the areas that we don't understand very well in organic dielectrics is what the parameters are that affect that breakdown voltage, that degree of partial discharge damage. It's certainly the case that the voltage waveform, as I've already said, plays a large part in it. However, we shouldn't rule out the fact that just because you've got a DC voltage, you can't have partial discharge, because of course, if you're switching that DC voltage, then you're effectively got a very slow square waveform. And so you will potentially get partial discharge every time you turn on that DC voltage and every time you turn it off. Pressure I've already talked about, that could be an important aspect. We don't really understand the effects of temperature very well, particularly in the range of dielectrics we're likely to be dealing with within our industry. Humidity is always, again, and quite honestly, we don't understand which way humidity will affect. Obviously, organic materials will take up moisture depending on the humidity condition. They'll change their moisture content, but how that affects their PD performance is largely unknown. And then, of course, you've got the issue of contamination, and that may well be affecting surface insulation resistance by inducing electrochemical corrosion, which may in effect also change the PD response as well. Oh, I've done that one already, my apologies. We've done several projects in this area. The first one we did was working with Aerospace HV, where we were looking at antenna systems to try and measure these partial discharges. What was attractive in that project was that we looked at a PCB-based antenna system, which could be used inside enclosures, etc., to measure PD within those systems. And we measured that alongside more conventional off-the-shelf antenna systems and monopole systems that we built. Our test vehicle, which is the one we've done most of our work on so far, is this twisted weld pair. And that represents the windings inside a motor core. But what that project did show us, that there was definitely a change in the PD occurring as we reduce pressure. These show the antenna waveforms, so the signal the antenna's picking up, so they're not directly associated with voltages, etc. But you can see that the energy of these PD discharges is clearly increasing as we decrease the pressure. And we went down in this case to about 0.3 bar, which is a typical civilian aerospace cruising altitude. So we have built this single channel system at the moment, which involves an amplifier system which can go to 5 kilovolts, a vacuum chamber here which we can take down to about 0.1 bar with appropriate pass-throughs. We're also measuring simultaneously the insulation resistance of the system as well, because we want to understand how that insulation resistance drops off as we age the system, age the materials within the system. And what's not shown here for some reason is the waveform generator. The whole thing, as you can imagine, is inside a very large cage with interlocks on it, and we probably spent more time going through the health and safety assessment of this than we've actually done any work today, but hopefully that will change. I should say that we are developing a 4-channel system as well at the moment, so we're looking to switch, maintain the aging through the amplifier across 4 samples simultaneously, and then periodically switch in the source meter to measure the insulation resistance as we go through the aging process. So this shows that PD within a simple twisted wire pair. This is a sinusoidal 500 hertz signal. That's the green signal. That these graphs are not brilliant for display, but they're nice colors. But essentially, we're seeing an inception voltage there. So that's the PD is the yellow signal in the background, and you can see these spikes occurring pretty much twice every cycle. As you go up through the sine wave and then back down through the sine wave, you're seeing these spikes occurring. They occur somewhere around just under 4 kV peak to peak, which is about a 1300 volt RMS with this particular sample. So it's above 1000 volts, but it is still below 1500 volts RMS, which is an interesting figure, which we'll talk about a little bit later. Once you set the PD up, it actually continues as the voltage drops. And so in this particular sample, the extinction voltage, that's the voltage at which PD stopped being measurable, was down at 3.2 kilovolts peak to peak. And at this point, this sample's got an insulation resistance of about 50 gigaohms. We then aged that sample. In this case, we aged it with a sinusoidal waveform for 1 kilohertz frequency. We set the voltage to 3.8 kilovolts peak to peak, which is slightly above the inception voltage, just so we got continuous PD discharge. And the insulation on those twisted wire pairs broke down to less than 10 megaohms in about 8.5 hours at 1000 hertz. And we're continuing this work at the moment. I've got other examples we don't have time to look at today, but what we want to try to understand is what effect this frequency has, what effect, how much over voltage we need to put on, what effect the atmospheric pressure has on this degradation time, and also what the waveform effect has, and particularly the rate of change of voltage with time. What we've also done is taken some samples that we've been doing fairly standard SIR testing on. So this is a standard test vehicle that we call this our TB33, but it's very similar to the B24, is it, test pattern. And we've coated it with in this case, one of them, a normal conformal coating, industrial standard conformal coating. No names, no pack drill. We've aged it in a normal SIR test for at 50 volts DC, both measurement and conditioning, in an 85 environment for 1,000 hours, and you can see that the SIR holds up above 10 to the 11 throughout that test. There's no flux on this PCB. If you put some solder paste underneath here and reflow before you coat it, it probably drops down to somewhere between 10 to the 9 and 10 to the 10 ohms, but you don't see, generally speaking, over a 1,000-hour test, any degradation in the system. Similarly, if you test that coating for a dielectric withstanding voltage, which is 1,500 volts AC for 1 minute, it doesn't exhibit any disruptive electrical discharge. There's no flash over, there's no spark over, there's no breakdown. You measure the leakage current, it's less than 10 microamps, and that passes the IPC ASTM standards for coatings. If you do a dielectric breakdown voltage test on it, it'll go to 7,500 volts without too many problems at all. So it's there quite happily. If you start to put a square waveform, in this case, across it, this is just at 50 hertz, you can see partial discharge occurring periodically through the system. And that's got an inception voltage with this square waveform of about 3.6 kilovolts peak to peak. This shows a 1 kilohertz sinusoidal wave across the same sample. In this case, it's inception voltage to start the PD. You can see the PD is a lot more noisy here. It's beginning to occur at different parts of the cycle as well, basically because our amplifier is struggling to drive nearly 4 kilovolts at 1 kilohertz. And we're in the process of upgrading that, hopefully. But anyway, that's talking about 1.3 kilovolt RMS. So that's not far above the 1,000 volt DC systems that we've been playing with now for a couple of years. And you can see lots of partial discharge occurring with this higher frequency system. So what we then did was run a simple sinusoidal 50, it's actually a 1 kilohertz sample at 50 volts it's already been aged at 1,000 hours, but we didn't see any surface insulation resistance, but we ran it with a 4.2 volt peak to peak, kilovolt peak to peak, which is just under 1,500 volts RMS on a sinusoidal waveform. And that's what happened after 5 minutes. So this is below the dielectric withstanding voltage. It's well below the dielectric breakdown voltage for this coating. Literally, I mean, 5 minutes surprised us, I will admit. We were thinking it could be some hours before it failed, but it went from, let's say, about 10 to the 12 ohms down to about 12 kilo ohms within 5 minutes of testing it at less than 1,500 volts RMS. So to that end, we will, that was just a test vehicle that we had standing around. Sorry, that's our standard test vehicle. It's a 400 track 200 gap test vehicle. Other people have done work. There's a lot of work. There's some work being published out of Manchester, which uses a test vehicle with these curved tracks with a 250 micron gap, looking at a range of coatings. We're still evaluating what the gap should be, but we'll probably follow this broad PCB design. We still need to do some work, we think, on this gap here. So if anybody has advice on what typical gaps they're seeing on it and any power PCBs they're producing, we'd be really happy to talk to people about that, because You know, it's all very well, we can do an academic exercise here and say that this gap is going to be a 1/4 millimeter, but if everybody in practice is going to use a 1 millimeter gap here because of electrical isolation rules, then maybe we want to be looking at bigger gaps than this. We've got 3 coating suppliers already on board. You'll supply us a variety of coatings to put over the top of this PCB, but as I say, we do welcome comments on tracking gap options, copper thickness, material specs, etc. The other thing we potentially like to do is look at via breakdown. We've done this with 1000 volt DC previously, and we've seen significant differences between the breakdown at these higher voltages and what might be expected if you extrapolate from lower voltages. But at the moment, we're planning to look at, we have this simple PCB that ranges in wall-to-wall spacings from about 0.5 millimeter up to about just over 2 millimeters. We'll do some inception voltages on uncoated samples of this just to see what the inception voltage is within PCBs, but it will only be a single material on a single PCB fabricator. So ideally, if there are people out there that would be prepared to incorporate a simple test coupon, not this whole package, but maybe just one of these coupons into a test coupons on the outside of their builds, and send the coupons to us, we'd be able to do a wider range of materials, a wider range of build structures to get us a better idea of where the inception voltages are across these materials. This shows the DC data that we had, and as we see here, we've got the time to failure plotted against 1 over the voltage in kilovolts here. So when you do CAF testing at about 100 volts, you're out here somewhere. But when you start to increase the voltage, if you just extrapolate data from 100 and 250 volts down in a straight line, you're ending up here with earlier failures at 1,500 volts than you would do if you just did that extrapolation. Now, the conditioning of these boards is DC at 1,000 volts and 500 volts, but we are switching that DC voltage in every 15 minutes or so, or rather we're switching it out, the conditioning voltage out to do the measurement, and then switching it back again. So that's equivalent of very low frequency square wave. So what we're not sure at the moment, and this is pure hypothesis on my point, is whether there's any PD occurring potentially at these higher voltages, which is causing these premature failures of the higher voltage system. So, you know, again, if we can open a dialogue with people looking at fabrication variables, via spacings, copper weights, disrupted zones, etc., then we'd obviously welcome that involvement. So, you know, we are seeing higher and higher voltages being taken up within organic systems. It may be that the whole world just turns to ceramic for these applications, but the cost for that will be high. I think in the longer term, there'll be a wider range of lower value systems that are going to be required. And these are going to potentially want to operate at much higher voltages. Silicon carbide wants to operate at 1200 volts. It also wants to operate at 300 degrees centigrade as well, which is another area we're working on at the moment, is looking at interconnection options above 250 degrees centigrade. The aerospace industry is potentially very interested in this, not just for coatings and PCBs and motor windings, but also cables, because obviously they've got this a massive weight penalty in these applications. So you really want to get away with as little dielectric as you can. You want that dielectric to be as light as you can. So understanding the effect of these high voltage pulses at different pressures as well is very important to them. We don't really understand the acceleration factors at the moment, because what we don't want to do is try to test a 20-year lifetime over 20 years. We want to do that over a few weeks. So part of what we're trying to do here is look at these acceleration factors. They're going to be different for different materials. So determining how we calculate those and what they're likely to be is important to us. And generally the test methodology in this area is very dominated by ceramic technologies, and they may not be appropriate for the organic dielectrics that we're talking about. So I think, yeah. So my contact number's there. Those of you know me already, I'm sure you can pick up the phone and call me. I should mention my colleagues, Berjo, Adam, Joe, and Ling, who are all doing the real work in the background behind all of this. And thank you all for the opportunity, and thanks for your listening.
Thanks, Martin. It's a fascinating presentation. I'm sure we're going to hear a lot more about this with the rapid increase in high voltage applications. We do have several PCB manufacturers on the call, so if you are interested in helping Martin, then please do reach out. And say it would be good if the ICT can support MPL with this work. Okay, so just a quick reminder, if you have any questions for Martin or for Ken, who's going to give our next presentation, then please send them to me using the chat function in Zoom. We'll be asking all the questions at the end after we've had both presentations. Okay, so on to our final presentation. I'm pleased to be able to introduce Ken Klapproth to the call, to the ICT members. Ken is the CMO for CHASM Advanced Materials and is based just outside of Boston. CHASM Advanced Materials are a leading developer and manufacturer of printed electronics and battery materials based on proprietary carbon, nanotube and ink coating technologies. It's great to have CHASM on the call again, and Ken's going to be continuing our education from earlier webinars on advanced antenna materials with his presentation titled "Connectivity Remains a Challenge, How a New Category of Advanced Materials Enable Overcoming That Last Mile 5G Challenge." Ken, over to you.
Great, thanks, Emma. And thank you to everybody who's joining us from around the world. With many technological advances, it seems like it's always one step forward and then two steps back. As my first engineering boss would say, sometimes as engineers, we make our own mess. And this is certainly the case, I think, when it comes to the evolution of 5G. So today we'll be talking about the design challenges that have been imposed by 5G to electronic devices, and how new materials can not only make those new products possible, but also help bring many new ideas into reality. So stepping beyond the science and getting to the engineering. So we have a lot to talk about, so let's go ahead and get started. So if you think about the last mile in connectivity, it seems like it's always been a problem since the introduction of cellular networks. The first generation of mobile networks, which was retroactively dubbed as 1G, was launched by NTT in Tokyo in 1979. The coverage was poor, the sound quality was low, and the service was plagued by drop calls. I remember having my first analog phone, and it seemed like I had to be standing in the right location with the right tinfoil wrapped in the right location in order for that to work. Over the course of the last several decades, we've evolved from 1G to 2G. In 1991, the real introduction there, the cultural revolution to that, was SMS and multimedia messaging services. We went from analog to digital, but digital calls just meant that it was a binary drop. Instead of it kind of fading out, it just dropped. So still there was a connectivity issue. The universal mobile telecommunications service or system of 3G was still based on GSM, and it standardized network protocols so users could get data, roaming data, from anywhere in the world. This introduced the idea of data packets, and people started to rely more and more upon the network in order to deliver data. At the end of the 3G era, somewhere around 2007, is when the launch of the iPhone really changed the dynamic going forward. 4G was deployed in Stockholm as the long-term evolution, or LTE, which continues to evolve today. This brought about high-quality video streaming. HD videos, video conferencing. So mobile devices really needed to be specifically designed to support the 4G the protocols. Today, this brings us to 5G. And 5G has actually been in the making for many years. It boasts superior connectivity, promises to transform everything from banking to healthcare through innovations such as remote surgeries, telemedicine, and even remote vital sign monitoring that could save lives. In addition, 5G also promises connectivity that empowers the Internet of Things, a digital revolution, if you will, that could see billions of connected devices sharing data seamlessly across the globe. 5G relies on multiple frequency ranges for the mobile communications. So below 2G is suitable for indoor and broader areas of coverage, as the electromagnetic waves at this wavelength travel far and reliably through different objects. When you get to 2 to 6 gigahertz, the C-band combines coverage capacity in the so-called super data layer. But frequencies in this range are increasingly susceptible to interference from weather and from natural surroundings like trees and buildings. Frequencies larger than 6G, 6 gigahertz, support high bandwidth, but then they require line of sight, as even leaves on trees or raindrops can block and interfere with connection. As various frequencies are used to transport signals for different applications, specialized antennas are required. The millimeter wave range of 5G new radio requires line of sight connections to maintain the fast data connections that people are starting to rely upon and want to have delivered. And that's another reason for more new antennas, which I'll explain momentarily. So where 4G could be served broadly from cellular towers, the higher data rates and speeds for 5G mobility demand line of sight connections or point-to-point connections between the different devices. The result is that you need more antennas, and those antennas need to be closer to people. If we look on the factory floor, Industry 4.0 and Industry IoT promises new levels of productivity through unified connectivity of smart devices, people, and industrial processes. Each of these devices are connected to the network through an antenna. So to just put this in perspective, just for the two applications that we've discussed so far, smart 5G antennas and IoT antennas, they're projected to require nearly 60 billion antennas by 2025. That's a lot of antennas. So more antennas closer to people, more devices needing antennas. So we'll either be surrounded by a whole lot of wall warts, these wireless access points that you've come to see ubiquitously all throughout your buildings, or we need to find a way to hide those antennas in plain sight. So what does this mean for product engineers that are looking to launch their company's next generation's devices that rely upon the connectivity promise of 5G? For high data rate applications, 5G, as I mentioned previously, requires line of sight connections. This not only means more antennas closer to people, but also antennas in conspicuous locations. Both traditional and autonomous vehicles in the automotive industry look to 5G to enable real-time advanced safety systems, where the necessity is now to get high on the vehicle, which means leveraging untapped real estate of window glass. This is also the case when you're looking to guide signals around through Wi-Fi, municipal Wi-Fi, to go between buildings and into buildings, traversing from the outside of the building to the inside of the building. All of the glass is welcome real estate for people that are trying to design antennas for this application. And finally, for IoT devices that need to be smart, they need to connect and communicate in real time to other devices on the network. So adding antennas to existing devices requires claiming space either inside of enclosures where space is always at a premium, or applying them to the outside of the enclosure where seeing an antenna is not necessarily desired. So addressing these emerging design challenges would be difficult for traditional antenna materials. However, if antennas were transparent, these challenges could easily be overcome. So typically made from metals such as silver, copper, or aluminum, antennas conduct electricity in the form of radio waves. So strong conductors make attractive materials in this application. Also, you need to consider known as the skin effect. Radio waves will travel along the top surface of those conductors. The higher the frequency, the thinner the skin. And so you can actually support higher frequency transmissions through thinner and thinner materials. There are a few materials in the world that are both conductive and transparent. And there's a new category of material that's known as nanotube hybrids that delivers conductivity that's required and the transparency that's desired to make these new 5G applications possible and make these antennas disappear. Here's an example you can see of a transparent antenna and then one with a copper grounding plane, both operating in the same way. So before we talk about additional applications, let me first introduce you to the idea of the new category of transparent conductor known as a nanotube hybrid. This combines all the benefits of the materials that are being hybridized and also removes some of their implicit limitations. As I mentioned earlier, there's many materials in the world that are transparent. There are also many materials in the world that are conductive, but there are far few that are both transparent and conductive. So all transparent conductors need to balance the conflicting constraints of transparency and conductivity. Looking at the image on the screen, for traditional silver nanowire films, anywhere where you don't see the silver rods is non-conductive. So in this case, the silver rods that you see are conductive silver, and in between those, a spaghetti-looking material is actually carbon nanotubes that have been printed in a light solution in order to be able to show the differences between those. Increasing conductivity in this case could mean either adding more silver nanowires or increasing their diameter, which then lowers the VLT or increases the haze of the material. So you put more silver down, it gets more conductive, but it also becomes less transparent. So the nanotube hybrid overcomes this traditional couple between transparency and conductivity, and I'll explain to you how. There are some truly remarkable properties of nanotubes. Nanotubes are conductive, they're self-assembling, they're environmentally neutral. So when used in a nanotube hybrid, they make the open areas that are traditionally non-conductive in these films conductive. They also bind the wires together to prevent separation or breaking during bending. So you can support applications such as bending or thermoforming, flexible screens, for example, in cell phones. Even if the conductive rods were to break, the conductive redundancy of the nanotubes means that the signal can still be transmitted. Nanotube hybrids can actually achieve better optoelectronic performance with less conductors. So they are more conductive and more transparent than their commercial alternatives. To help explain a little bit the difference or the connection between transparency and conductivity, transparent conductive films have some rating of sheet resistance and transparency. In this case, it's measured in VLT. This rating is achieved through the interaction of the conductor density and the open areas remaining on the film to arrive at some prescribed value. One of the ways of making the film more conductive, as I mentioned previously, would be to increase the diameter of the conductor. So fatter wires carry more signal. So this will increase the conductivity or lower the sheet resistance as desired. But the unwanted side effect is that they are also easier to see, so transparency will be reduced. Another option to get this desired effect of increasing conductivity is to increase the density of the wires. Again, more wires carry more electrical signal, but more wires also have the unwanted side effect of being easier to see, so thereby reducing BLT. So for both options of thicker conductors or more conductors, you achieve the desired goal of better sheet resistance, but at the expense of reduced transparency. So by the way, when you add fatter wires, you also increase the probability of introducing unwanted haze that happens from reflected light. So since nanotubes are conductive, the nanotube hybrid makes all the open areas of the film conductive. This means that you can actually reduce the density of the conductor and still achieve the desired increase in conductivity. The nanotube hybrid is the only category of TCF that simultaneously can increase the performance of both conductivity and the transparency for both of these variables. Another thing you need to consider when making applications out of things like transparent conductors is how you're going to make a connection to that transparent conductive film. So both silver nanowires or metal mesh films are transparent conductors that are traditionally used in the industry, but the nanotube hybrid has some clear, and like that, this nanotube hybrid has some clear plastic substrate that's used. So in order to provide environmental stability to these silver conductors that are typically used, some form of overcoat is required for the silver nanowire or metal mesh films alone. This does provide protection, but it also serves to electrically isolate precisely the conductive layer that you need in order to connect to create your circuit. So creating a good connection for your desired circuit, in this case, requires bridging the gap by etching, abrasion, or laser ablation, which in turn exposes a path for environmental degradation to the silver down below. In the case of the nanotube hybrid, nanotubes that are dispersed in the nanotube inks are not only conductive, but they're made of carbon. Carbon is environmentally stable and it's even protective in hot, wet conditions. So the conductive redundancy of the nanotubes extend not only up to the surface, making it simple and robust to make connections, but also the nanotubes themselves form networks around the metallic conductors, so that if the wires were to break or to separate, the circuit is still completed by the conductive nanotubes. So desired finished circuits can be made from nanotube hybrids that are much simpler, faster, and more cost-effective to fabricate, plus offer the enhanced environmental stability and durability in the circuit's lifespan. So how do you go and make a circuit out of a nanotube hybrid? So unlike the commercial alternatives that require either laser ablation or photolithic etching, which are both expensive and time-consuming, nanotube hybrids are patterned using inexpensive and readily available screen printing techniques. So you start with a film, in this case, it's a metal mesh film. You then use standard screen printing techniques to print the shape of the desired antennae that you want, in this case, a monopole antenna. These can be repeated multiple times, so you can really cost effectively gang together and tile many circuits onto one sheet. Then a simple wet etching process will remove any of the exposed metal mesh areas that aren't desired, and you're left with the circuit, patterned TCF circuit in the desired shape that you would like. We have two versions of the nanotube hybrid materials that are available for antennas that are specifically designed for antenna applications. One of them is 1 ohm per square and offers 94% transparency or VLT. And we have another version that's 0.2 ohms per square. This has a slightly lower VLT at 84%, but the pitch on this is much finer, so it can support very fine level details. Here's an example of a near field communications antenna for mobile applications. This was fabricated as a collaboration with what we call our preferred integration partners. In this case, it was VTT Technical Research Center in Finland. This device used our Agent 1 Generation 2 nanotube hybrid for the transparent conductive antenna circuit. At 94% transmissivity, the circuit is visually transparent even when it's not backlit. Using commercially available hybrid electronics that VTT applied to the circuit, they used standard assembly and programming methods. There was nothing special that was required in order to produce this circuit, and it worked out of the box the first time it was created. Within days of receiving the screens that were needed in order to screen print this device, the finished transparent circuits were available for our collaboration partner VTT to finish the circuits themselves. And within days, they had working devices that were available. So this is a simple example of how nanotube hybrids fit into existing work processes that require little tuning or special training in order to successfully execute. For another Bluetooth application, the customer's goal was to add an antenna outside of the enclosure. So establishing a baseline, they established a baseline using a copper antenna. And you can see in the 360-degree polar view and also the baseline in the frontal view that represents the front of the device, the frequency response there. The nanotube hybrid antenna performed not only equal to the solid copper antenna as it was measured around the full 360 degrees around the antenna itself, but also produced higher gain across the angle represent the front of the intended device. So this really worked well in the customer's application. So regardless of the design requirements that you might have for your next generation 5G device, we believe that nanotube hybrids can deliver the performance that you need, plus the transparency that you desire in order to realize these inspirations. At CHASM, we like to say that nanotube hybrids enable the best flexible printed electronics that you'll never see. So thank you for your attention during the presentation. I hope you found this information both interesting and useful, and the presentation entertaining. So with that, I guess I'll turn it back over to Emma and open the floor to any questions.
Thanks, Ken. I say, as a materials engineer, I love seeing kind of work and development like this. I think it's really interesting to see some very practical uses there. Okay, so now time for our panel discussion. If you've got any questions, send them to me on the chat function.